Alright, so my target audience is a Intro to Computer Science class with freshmen and sophomores here at Augsburg. First, I'm going to start out by saying, let's be honest. Everyone has had to learn their ABCs ever since they were little. Everyone has to remember them for the rest of their lives, especially if you live here in America. But just like we have to remember our ABCs, so do computers. But computers don't learn like we do. And they have a concept of memory that is directly measured by a system called bytes. Now, there's various different sizes and kinds. Like, for instance, there's a megabyte, a gigabyte, a terabyte, a kilobyte, and all ranging in different sizes. Which brings us to our main point. How much memory does it take for our computers to remember a series of letters? Well, let's think about that for a while. First, I'm going to talk to you guys a little bit about three different parts. First, I'm going to talk to you about a little bit about my method for how I went about figuring this out, and like what my data was for drawing my conclusions. And then, at the end, I'm going to tell you guys a little bit about what conclusions I did draw from the data. Okay, so we live in an age where we have a vast store of memory at our disposal. We use everything from terabyte floppy hard drive computers to just basic terabyte external hard drives to store everything from millions of songs to hundreds of videos. We basically have an endless, well, not endless, but an extreme amount of space to store these things, especially if you own a laptop, whether it be Mac or Windows. They both store immense amounts of memory. But I think because we live in this age, we generally forget what it used to be like to not have as much memory in our computers. Which leads me to my second point, being that we need to look a little bit more in depth about what used to be the extreme for what can be stored on a computer. I'm not talking about your laptop, I'm talking about giant computers. Computers as big as your house. These giant systems were huge. In fact, they were powered by these little bulbs called vacuum tubes, and there were hundreds of them, and they would turn on and off depending on what information was being stored or processed. Okay, let's talk a little bit about my method. So for this, I came up with an 8-step model, and my 8-step model has a setup. All you need for it is your laptop, a text document of some kind, whether that be Notepad or Microsoft Word or any of these other things. And you'll need an external or online database to cross-check your data, so you know it's not incorrect. Alright, let's start with my method. What steps of my method are there? Well, the first step is you go to your computer, you go to the Start menu, you search Notepad or TextEdit, you open it, and then you insert the desired variables, desired amount of letters, and you store it. So you save it using the File menu button at the top left corner of the document, and then you save it to your desktop and rename it whatever experiment number it is. Then what you do is you take the file and you right-click on it, and you go to Properties. Once you click on Properties, it'll bring up a screen that will show you just how many bytes of storage each of these things uses. Sorry about that. Camera's being weird. All right. So let's talk about it. All right. So after renaming your file and finding out how many bytes it uses, you drag that file into your online database, which I use Dropbox, and cross-reference it to make sure that whatever's being stored in the online database matches what's being stored on your laptop. So if it says like 26 bytes, for instance, then if you drop it into an online database, what I'm using is Dropbox, and it says something different, that means that the file is not as big as the computer was telling you, which means you need to either redo the experiment or change your variables. Alright, then the last step is to repeat the first 8 steps. Okay, so that said, what findings did I have? Well, my data shows, as you can see here on my invisible screen, that you can't see right now because I don't have a PowerPoint. My first experiment, my whole sets of data is I only did 11 experiments. Each one of these experiments, I changed one thing about what I stored in the text document. Like, for instance, in the first one, I stored all the letters of the alphabet, and then I saved it. And it turns out that it was stored as 26 bytes. Now we can draw conclusions right from that right away, but I'm not going to right at this moment. Now, my second variable, I only stored one letter, and I only got 1 byte left when I stored it, and that's no spaces. Alright, so as you see in the variable section of my graph, of my flowchart, you can directly see what variables I changed and stored in each text file. But what can I conclude from my data? Well, I can conclude a lot of things. In fact, a couple of the things that I can conclude is that capitalization really doesn't matter. If you stored letters, if you store letters in the text document and they're capitalized, they'll be stored with just as much space as they would normally be if it's in a text document like Notepad. Also, the second conclusion I can draw is spaces matter. Now, when I say spaces, I don't mean like, oh, there's a space that's being stored. That's kind of true, but not exactly. When I mean space, I mean when I was typing the letters inside the text document, I hit the space bar, which put a space in between the letters. Now, if we save that space into the text document, that will count as a bit of information. That bit of information is just as valid as the rest of the other letters or characters, just because it takes up that space. So this can be concluded through experiences 1, 5, 7, and 6. In each of those cases, the spaces were directly coinciding with the amount of bytes that were being stored. For instance, when I stored 26 different letters, the entire alphabet, and then I put an extra space in, I ended up getting 27 bytes of information instead of 26. That leads me to believe that spaces can be stored with just the same amount of space as letters. Alright, now my third and final conclusion that I can draw from my data is the number of characters, and how I can draw a conclusion about that, about the size of a single letter. Through experiments 3, 4, 7, and 8, even 3 and 5, how many ever letters I put in, whether capitalized or not, I only got what 1 byte of information stored for each. And that can be and that's directly related to each of my experiments total. Nothing coincided with it. Okay. Are there any questions?